Hello everyone. So today we are solving a question of JEE 2020. This is from the topic of properties of matter, and we can say this from specifically from the topics of properties of thermal properties of matter. And this is one of the most underestimated topics. People consider it for JEE mains and do not take seriously for JEE advanced. So here's an example how the JEE advanced can use these topics to make a difficult question. So let's read it. So they're given a filament of light bulb which has surface area of 64 millimeter square. It is can be considered as a black body which is at a temperature of 2500 Kelvin, emitting radiation like a point source. When viewed from afar at night, the light bulb is observed from a distance of 100 meter, and the pupil of eyes of the observer are given as some radius. So some constants are given like Stefan-Boltzmann constant, Wien displacement constant, and the Planck's constant and speed of light. So what we have to find first, the power radiated by the filament, then the radiated power entering into the eye, the wavelength corresponding to the maximum intensity, and taking the average wavelength of the radiation to be this. What is the total number of photons entering per second? Okay, so let's start the question. Before starting the question, I must mention the most important formula used here. It will be sigma A E T to the power 4 is equal to the power emitted or the energy radiated per second, that is P. So here epsilon is nothing but the Stefan-Boltzmann constant itself. A is area, E is the emission ratio, and for the ideal black body, E is always equal to 1. Okay. Now T is the temperature given and P is the power radiated. So as for the first question, we can directly apply this formula, and how we can do it, 5.67 into 10 to the power minus 8 multiplied with the area of 64 into 10 to the power minus 6, and if we multiply it with T to the power 4, that is 2500 to the power 4, 2500 into 10 to the power 4. So you can see how much calculative it is, and you have to give your very much time here. So let's first we'll calculate it. 10 to the power 8 and 10 to the power 8 can be cancelled here, so it will can be written as 25 to the power 4 or 625 square into 64 into 5.67. So we can say 625 into 8, we can calculate first. 625 into 8 is nothing but 4800, 4960. So it is 5000. It will be equal to 5000. And if we do 5000 square, it will be again 5.67 into 5000 square is 25 into 10 to the power 6 into 10 to the power minus 6. Here, cancelling all of this. See how quickly I did calculation, because like I found that they both are square. I combined them with 625 into 8, then again did square, so it become very easy here. 5.67 into 25, it will be somewhere around 25 into 125 plus 25 into 67. I need to calculate this. Now 25 into 7 is nothing but 140, 175. Okay, and 25 into 6 is 150. So 5761, doing all this, so we can get it as somewhere 141.75. So yeah, this is the power radiated, and I don't think that it is matching to our given option range. Hence, we can declare our option as incorrect. Now, moving on to option B, what is the radiated power entering into one eye of the observer from this to this range? So, to do this option, what we have to consider is intensity. Suppose this is the point source. Okay, let me first imagine this question, and let's suppose this is the region. Okay, like it should be at the center. Hmm. Hmm. Like this. Okay, if this is at the center, now at some this radius 100 meter, that don't consider it circle, it is like spherical because it's in a region. Okay, so at this point, what will be its intensity at like this, some cone or solid steradian angle? So how can we calculate this? It is nothing but the the power given by the net surface area. It will be divided like this only, so 4 pi r square. Okay, it will be equal to 141.75 by 4 pi into 100 meter square, that is 10 to the power 4. Now when if it is entering someone's eye pupil, so we have to consider that these rays are entering somewhere like this. So some part of this intensity will be multiplied with the what is pupil's area. So pupil's area can be given as 3 millimeter, which means the pi times 3 millimeter square, that is 3 square into 10 to the power minus 6. Let me, yeah, 10 to the power minus 6. So now if we calculate pi cancel, so 10 to the power 4, it becomes 10 to the power minus 10. 3 square, 9 by 4. What is 9 by 4? It's nothing but 2 point, I think 2.25. Yeah. So 141.75 into 2.25 into 10 to the power minus 10. If we do it, okay, let me do it properly. Can I use calculator? Yes, I can. Like I can do it with hands also, but let me use 141.75 into 2.25. So it gives us around 318.93. Okay, 318.93 into 10 to the power minus 10. Now if we want to match with our option format, so it will be somewhere around 3.18 into 10 power minus 8. So is it matching our option range? Let's see. Yes, absolutely. It is between 3.15 and 3.25. So we can mark our option B as correct. Now the wavelength corresponding to the maximum intensity of light is 1160 nanometer. How to calculate this? So if you remember Wien's displacement law, what is Wien's displacement law? Wien's displacement law. It says that lambda m times t is equal to a constant which is called as Wien's displacement constant. So let's write what is lambda m. Temperature given here is 2500 and our B is nothing but, where is our B given? B is given as 2.90 to 10 to the power minus 3. So 2.90 into 10 to the power minus 3 divided by 2500. So what it will give us? 2.9 by 25 into 10 to the power minus 5. So 2.9 divided by 25 is somewhere equal to 0.116. 0.116 into 10 to the power minus 5. Like you can do this calculation. Again, we can take it as 1160 into 10 to the power minus 9 or 1160 nanometer. So yes, it is absolutely matching our option C, as we can mark it as correct. Now given, taking the average wavelength of the emitted radiation to be 7740, the total number of photons entering per second in one eye, and the observer range is somewhere from this to this range. So to calculate this is nothing but given power only. Like we can write power as, what is power? Power is energy per unit time. Energy, here energy is the light energy. So we can say like photons are entering. So P is equal to, what is energy of a photon? It is h mu, and n photons are entering per second. So this is our whole equation. Okay. So mu is not given, so we can use C by lambda. Yeah. So let's calculate the what are the number of photons entering per second in the pupil's eye. So for that, what we have to take? We have to take this power which is entering in its eyes about like, because we will write exact value, that is 3.18 into 10 to the power minus 8 is equal to okay, n we have to find. H is nothing but 6.63. Oh yeah, 6.63. 6.63 into 10 to the power minus 34. Now speed of light is somewhere around 3 into 10 to the power minus 8. Sorry, 10 to the power 8. Now by lambda is given somewhere around 1740. Yeah, 1740 nanometer. See, again, this is very much calculative. I need to use calculator for doing quick calculations. You don't have an option. So let's multiply. 1740 nanometer can be written as 1714 to the power minus 9. So if we calculate all of this, so 3.18 into 1740 divided by 6.63 divided by 3. Okay. So we get somewhere around 278.19. And now we have to adjust all those powers. So 10 power minus 16, and it will go multiply. So 10 to the power minus 16, 9 is 25 into 10 power 34. Now if you do this, you will get somewhere around 2.78 into 10 power minus 11. So which is also matching our option range, and we can mark it correct. Hence we get option B, C and D as our correct options.